Interactions in VR these days are usually done by using a controller or optic hand tracking. However, those gesture input methods have severe limitations compared to real-world object interactions. We use our sense of touch to navigate and understand objects in the real world. By adding the sense of touch to VR interactions, we could greatly improve the engagement of virtual object manipulation. This diagram shows the key components of a haptic glove system. We have the motion capturing glove to capture the finger movements. The captured hand model will then be rendered in a VR environment alongside with interactable virtual objects. Haptic feedback will be rendered according to the virtual object's haptic property. For example, whether it is a hard 8 ball or a soft balloon. There has been many approaches to making haptic gloves. However, there are some challenges. Many state-of-the-art haptic gloves are big and bulky, for example, exoskeleton gloves. So we have chosen to use lightweight sensor and actuators for our glove. Our glove uses dielectric elastomer strain sensors to capture the hand gesture. And for vibrotactile feedback, most devices use motors with resonant mass, which has a fixed vibration frequency. This limits the amount of haptic information that can be communicated. So we have used piezoelectric motors that have a wide vibration bandwidth. Hardware is just one of the components in a haptic system. Haptic rendering also plays a huge role in the perception of touch. We have transcribed 4 real-world objects, which were the metal, tennis ball, silicon elastomer, and balloon. The compression properties were measured on a load testing bench using a soft biomimetic finger indenter. The raw force data was processed using polynomial regression, and their force intensities were normalized. Each material uses a different vibration frequency. A higher frequency tends to feel harder, while a lower frequency feels softer. Elastic objects in real life will deform under compression, so we have included this material property for virtual objects. For example, the virtual metal ball does not have any visual deformation when squeezed, but for the tennis ball, silicon, and balloon, they will have different degrees of deformation when pressed. Our key contributions include the approach to make a lightweight vibrotactile glove with high feedback frequency bandwidth, and a novel method to transcribe real-world compression into haptic cues. We have conducted user studies to investigate the visual haptic interaction in virtual material discrimination tests. We plan to use our glove as an experiment platform for future user studies, such as more sophisticated rendering methods, for example, different textures, or integrating the current vibrotactile feedback with kinesthetic feedback, and also making VR applications and games. Now please enjoy the video demo of our work.